In our previous video, we defined a Pythagorean triple as any triplet of values that satisfies Pythagorean theorem, and specifically all of those values are integers. Now, there are non-integer values that satisfy a squared plus b squared equals c squared. We've seen many examples of that in our explorations in maybe geometry class, but Pythagorean triple will be just those ones where a, b, and c are all integers. Now, a primitive Pythagorean triple, as we defined, is a Pythagorean triple, so all integers, but they have no common factors, meaning there's no number other than one that divides all of them. So the questions that we wanted to ask were, well, how many such triples are there? Okay, let's start with that question. And it turns out that this is almost a trivial answer, and the answer is there are infinitely many. Okay, and here's why. Let's take a look at just the formula 3 squared plus 4 squared equals 5 squared. So we'll explore this by example. Now, one thing that we know about products involving squares, and I just want to emphasize this property for a moment, is that if you take a times b and you square it, well, what that means is a times b times a times b. Order of multiplication doesn't matter, so you get a times a, it's a squared, times b, which is b squared. And so a product squared is the product of the squares. Square of a product is the product of multiplication of their squares. Okay, that's going to be helpful because if I take any number and multiply both sides by it such that it can be written as an integer squared. So for example, let's say that I multiply both sides of this equation by, let's pick 2 squared. Okay, in that case, I distribute this to all three terms on the other side of the equation, then I get 2 squared times 3 squared. Well, by this property, the product of squares is the square of the product. So I can actually write this as 2 times 3 quantity squared plus 2 times 4 quantity squared equals 2 times 5 quantity squared. And now I've just generated 6 squared plus 8 squared equals 10 squared. And you can verify that 6 squared plus 8 squared gives you 100, and 10 squared also gives you 100. So we have actually found another one. Now granted, this is not a primitive Pythagorean triple, because notice that now each of these numbers has a factor of 2 in common. But this at least helps us generate the fact that there are infinitely many Pythagorean triples. So there are infinitely many, and if you have this formula, a squared plus b squared equals c squared, and just now symbolically, let's say we multiply both sides by d squared, some other integer, well then we can write that as a times d quantity squared plus b times d quantity squared equals c times d quantity squared. And d could be any integer. D is any integer, and therefore, since d is any integer that you can choose, there are infinitely many Pythagorean triples. Now, as we're going to show, there are also infinitely many primitive Pythagorean triples, but not for the same reason. We can't really do that because like I said, we're introducing now all three of these numbers have a factor of d in common, where d doesn't necessarily have to be 1. Okay, so we'll come back to this question. How do we answer this? Well, we're going to actually see a little bit later why there are infinitely many. Okay, how can we begin searching for these? That's an interesting question. Most things are done on technology, using technology these days, and it is nice that we can actually generate them. So here's sort of the idea. Let's say that we just start off with a table of values for A, B, and C. And this is just sort of the brute force way that we could do it. We could start A at 1 and then check then put b at 1, and then put c at 1, and then ask ourselves, does a squared plus b squared equal c squared? Okay, and so of course 1 squared plus 1 squared is not equal to 1 squared. So then we would put no. Okay, so we know that that's not a Pythagorean triple. Now the next thing we could do is we could just, what about 1, 1, 2? And that again is going to be an answer no. And then 1, 1, 3, and kind of keep trying these. This is, like I said, a brute force way until maybe we set c to go up to, I don't know, we'll say c goes from 1 to 100. And then once we get to the point 1, 1, 100, and find out that's a no, maybe what we now do is we advance the value of b. So we check 1, 2, and now we go 1, 2, 1, 1, 2, 2, 1, 2, 3, all the way up to 1, 2, 100. Now I've written a little procedure to do this for us. This is in Python, and this is going to do precisely what I just described. We're going to write a loop that's going to select values of, okay, we can make this A, B, and C. And it's going to start off A at 1, and then it'll select B to be 1. Well, it'll be the value of A. And so then we're going to check the value of C. So we'll have 1, 1, 1, 1, 1, 2, 1, 1, 3, etc. And we'll toggle through all the values of A and B. So A, B, and C. So what do we want to check? We want to check how you do a square in Python. It's star star as opposed to caret. And if a squared plus b squared is equal to c squared, and also we want to check the GCD, the greatest common divisor between a, b, and c. So don't get too wrapped up in why I've done it this way, but I'm just checking to see that the greatest common divisor, the only number that divides into all three of these integers, is 1. If that's the case, then we found a primitive Pythagorean triple, a, b, and c, and we're going to print it. So if we run this, you can see there's 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 20, 21, 29. So we found 4 such that a, b, and c are in the range from 1 to 30. Okay, if we omitted this condition right here, I'm going to comment that out and just write it like this, then we're going to get more of them, because notice 6, 8, 10 is a Pythagorean triple, but it is not primitive because 6, 8, and 10 are all divisible by 2. Similarly, we could go down the line, 9, 12, 15, that's a Pythagorean triple. It is not primitive because 3 divides 9, it divides 12, and it divides 15. So 10, 24, 26, 12, 16, 20 again. Even 15, 20, 25, these guys are Pythagorean triples. They are not primitive Pythagorean triples. So let's put that condition back in there. That way we're just focusing on primitive ones, and we get a smaller subset of them. Okay, so that's how we can generate these values. We can create this sort of routine that will do this for us. We can also keep on going. We can even set these, say, up to 300. This might take a couple of minutes to run now. It's going to become less and less efficient. See, it gets slower, and we are generating quite a few of those. So I think we're done running now, and so there we've generated all of those. You can see that it's not highly predictable as to how many there will be. Great. So we know we can generate them. We're convinced that there are infinitely many Pythagorean triples. We're going to convince ourselves that there are infinitely many primitive Pythagorean triples as well. Now let's try to understand the structure of these triples. So we've hopefully studied some number theory up until now. We know something about even numbers and odd numbers. So let's focus now on the structure of these numbers. Let's consider the different types of numbers that a, b, and c can be. So even and odd. Okay, so if we consider a, b, and c, and then we consider, can it be a primitive Pythagorean triple? establishes that they can't all three be even. We know that there are Pythagorean triples like 6, 8, 10, all three even numbers, but they're not primitive because they have a common factor of 2. So if these three are all even, then it is not a Pythagorean triple. Now, the other possibility is where A and B are even, but C is odd. So even, even, odd. Well, the problem that we'll have there is that if we take an even number squared plus an even number squared, we're going to end up with an even number. But if we square an odd number, we know that an odd number times an odd number is an odd number, and there's no way that the left-hand side, which would be even, can equal the right-hand side, which would be odd. So it's not possible. In fact, this is not even a Pythagorean triple, but we concern ourselves just with primitive Pythagorean. So the other possibility is where okay, A and B cannot both be even. Can they both be odd? Okay, well, there's the possibility that they're both odd and that C is even, and there's the possibility that they're both odd and C is odd. So if we even delve back into the ones that we've generated before, one thing that I'm noticing here is that it seems that at least one of those elements in the triple is going to be even. 264 right there, and the primitive Pythagorean triple 23, 264, 265. Here's an even number, even number, even number. And it seems like all of these are going to have either A or B be even. Notice that in none of these cases, none of these values of C are ever even. It always tends to be either A or B. Not both A and B. So it seems that it's never going to be the case that, based on what we're experiencing, that A and B will both be odd. Well, let's are both odd. Let's say A, B, and C are all three odd. Okay, so if we analyze that, and I'll label this as row 4 here. If we analyze row 4, that would imply that we have an odd squared plus an odd squared plus an odd, equals an odd squared. By the structure of an odd number, that would mean that A has the form 2k plus 1. An even number plus 1 is an odd number. And if you square that, and B will be able to form 2j plus 1 squared, and C would be able to form 2m plus 1, where k, j, and m are all integers. So let's see what would pan out here. If I do a little bit of distribution here and try to analyze this, I'd have, well, wait a minute. First of all, if I take an odd number, I square it, this is going to be odd. 2j plus 1, if I take an odd number times an odd number, that's going to be odd. And now I'm summing two odd numbers. Odd number times an odd number is going to be odd. But if I add together two odd numbers, I get an even number. And there is just no way that an even number can equal an odd number. So that means that this is not a possibility. It can't all three be odd, so that's good. Can C be even? Well, let's analyze that. I'll call that row 3. Well, that would imply that we have 2k plus 1 squared plus 2j plus 1 squared. Now, since we're looking at C being even, that would mean it is of the form 2m. So if I do some distribution on this, I'll get 4k squared plus 4k plus 1 plus 4j squared plus 4j plus 1, and that would equal 4m squared. Okay, now if I combine some like terms here, I get 4k squared plus 4j squared plus 4k plus 4j plus 2. Okay, now everything seems okay so far. There doesn't seem to be anything unusual here. I have an even number on the left, I have an even number on the right. But here is something that will disprove this from being a possibility. If I divide both sides by 2, in other words, if I take 1/2 of both sides, it'll be totally okay. We'll still be dealing with integers. That'll just give me 2k squared plus 2j squared plus 2k plus 2j plus 1 equals 2m squared. Now here is where the contradiction lies. I have a bunch of terms that have a factor of 2. I have 2 times an integer, and then I have plus 1. On the right-hand side, I just have 2 times an integer. So, and I'll just call this integer 1, and this is integer 2. Okay. Now, over on the left-hand side, this is actually an odd number, and over on the right-hand side, I have an even number, and once again, these cannot be equal to each other. So this is a definitive no. Now, I could do the same thing for, by the way, we don't need to toggle A and B. We don't need to say even, odd, odd, even, because A and B are, it doesn't matter what order you write them in, whether you write A squared plus B squared or B squared plus A squared. So I don't have to say even, odd, and consider the situation where I have A odd and B even. So we're not losing any generality there. The reason we don't need to consider that is, again, because they're being added together. So it's still going to be an even squared plus an odd squared, whichever order A and B are in. So all we really need to do is consider even, odd, odd, and even, odd, even. Now, in this case right here, where we take A being even and B being odd, that means we're going to square an even number. I'm going to just kind of talk through this. So think with me. If I square an even number, it'll be even. If I square an odd number, it will be odd. An even plus an odd is an odd number. Anytime you add any multiple of 2 to an odd number, you still have a number that divided by 2 has a remainder of 1. So even squared plus odd squared will be odd, but then an even squared on the right-hand side is even, and an odd cannot equal an even. So that's a definitive no. Now, I'm not going to go through this here, but the same kind of logic would hold. If we let A and B both be even and odd, and C be odd, then we would actually run into no problems with that. In fact, let's just go ahead and just to verify that this is not going to give us the same type of contradiction as we encountered up here. To analyze number 5, I'm taking an even squared, so 2k squared plus an odd squared, which is 2j plus 1 squared, equals an even squared, which is 2m squared. And that means here I'll have 4k squared plus 4j squared plus 4j plus 1. And here I forgot to put the 2m plus 1 in there. It's an odd number. And so here we will get 4m squared plus 4m plus 1. Okay, well, there's nothing that there's no common factor on the left and the right as far as being able to factor out 2. I can't do that. I get an odd number on the left and I get an odd number on the right. That is clearly okay, and so it makes sense that one of our factors is going to be even and the other one is going to be odd. Now, it doesn't, again, matter whether A is the even and B is the odd, or B is the even and A is the odd, because you can see in some cases B is even, in some cases A is even, but there's always only one even number. So here we can have even and odd, but C is always going to be odd. We could also have A is odd, B is even, and C is odd, but like I said, that's just a redundancy because what we call A and what we call B is pretty much arbitrary. So there we go. So we know that every single primitive Pythagorean triple will have A, B, and C being odd, even. Okay, so here's what we have so far regarding primitive Pythagorean triples. We'll stop here in this video. Suppose we have a primitive Pythagorean triple ABC satisfying A squared plus B squared equals C squared. Okay, All we're doing here is we're just building what we know about such numbers, such triples of numbers. It follows that A is odd, B is even, and C is odd. And A, B, and C have no common factors. Our next question that we're going to aim to answer is, how do we begin generating these numbers mathematically?